Okay, let's start out. Welcome back, everybody. We're going to continue with this conversation using the normal distribution. We're doing a couple things right now. And so it might seem like we're just teaching you algebra, teaching you a little bit of calculus with avoiding the calculus, and showing you how to work through these posteriors. I'm also teaching you what a gift sampler is without telling you yet. And so these distributions that we're working through are going to be useful in the future. And so you might think, it's a little too contrived if I say I give you sigma squared. Why not just jump to the full-blown thing? This is a step in a bigger process. This one seems even funnier, because you've probably never seen this, where we're going to assume you know what mu is. Again, we're working with the normal distribution just to give us some familiarity with a problem we already know about. But this is a little bit weird. Let's infer sigma squared given that we know mu. You might know how to do that from a different class. You've probably never done it. You know, probably just something that shows up in the textbook. So there are some practicalities, but we're getting into the rhythm of things. So likelihood times prior, what's the likelihood function? What are conjugate priors? What are the limits of these things? What are the properties of the distribution? So something I want you guys to do throughout the semester is anytime we invoke a distribution or we talk about it, I want you to go to Wikipedia and look it up and read about it. Even just the little box on the side is probably good enough, and seeing some of those pictures. Knowing your distributions, what their properties are, what they do, where the parameters live, how those distributions are shaped, I would say is the fundamental key to being a smooth, swift Bayesian. And so we're always writing down likelihood functions. So we know what the distributions look like, we know what their parametric forms are, and we know what their properties are. And so people that don't know that, like let's just say a t distribution. How many people know what that distribution looks like? And what I mean when I say that is, could you write down its density function? Like Jenny's like, man, I know what a t is. That's what they teach you in 101. And she probably just thought for the first time, you know what, I have no idea what the density function is. But we use t's all the time in all stat classes. So I remember when I was an undergraduate and I was taking my first probability class, and I had asked, like, what does a t density look like to a stats professor? And he didn't know. You know, and I think that's kind of funny looking back. All Bayesians would know this off the top of their head because we use it all the time. So get acquainted with those densities. They'll make everything really easy for you. Recognizing what the densities are, what the distributions are, figuring out what the conjugate priors are, requires you to know what the density functions or probability mass functions are in the first place. So do that regularly throughout this class. If you find a new one, I recommend writing it down, putting it on your refrigerator, writing down the properties right next to it. And the reason I pick the refrigerator is because it's the place that you're at least aware most often in your house. You go to your refrigerator how many times a day? How many times do you go to your refrigerator a day? At least like 10, right? I go like 20 times. I go and I get water out of my refrigerator all the time, right? Grab a piece of cheese and snack on it. So when you do that, look at it on the refrigerator and just kind of glance over it, and that's how you learn. Repetition is the key to learning, if you didn't know that already. So you're never going to be able to cram that stuff in. You'll just get confused. So try that throughout this class. It will make a big difference. Simple strategy. Okay, we'll see a little bit of that in this lecture. Again, we're playing around with n is equal to 1 for now, but we'll change this all to n is arbitrary later on. We'll see kind of the performance of everything. We won't play around with n greater than 1 today. There's a point I'm going to make a little bit later. Okay, so we see something from a normal distribution. Normal distributions, xi's live between negative infinity and infinity. I guess somebody might mark if I put the square bracket on there. Unattainable, it's just a concept. Mu lives in the same place, so it lives between negative infinity in infinity. And where does the variance live?
0 and 1.
Yeah, it's positive. So you might say between 0 and infinity. You might include 0 in there. You know, but you'll kind of notice you might be dividing by 0 in some places that might mess you up. Also, if a random distribution had no variance, it's not actually varying. Now, mathematically, that is still a distribution. A point mass is a distribution in itself. No proof required, it's just a fact. So Dirac spent a lot of time grappling with this, though. But it's probably not the most interesting one. And if things have no variability, there's no need to do stats. Okay, so I want to say a little bit more about improper priors. So in improper prior, so I'll say pi theta, just to be arbitrary. Let's just imagine it's a density function. Theta lives somewhere. I could tell you where it is. Let's just write it down arbitrarily. Theta lives in some space. So if I'm just trying to be arbitrary, I'll write something like that in there. This means element of. Most of you are familiar with it. This is just some space right here. Theta lives there. That's the polite way to do things. I sometimes omit that, and it's okay to ask me where the parameters live. So an improper prior, and I should just say a distribution. It doesn't have to be a prior. I've never seen these used outside of Bayesian. And so usually they come up in the context of Bayesian priors. Other people, you're never going to do inference off of an improper distribution because it doesn't integrate to anything. And so what we're interested in is usually figuring out how much mass is in a certain interval, how much of the area. But if it integrates to infinity, whatever that mass is always going to be negligible to what's happening in the tails of the distribution. So an improper distribution, where my bounds of support are this, has the property if I go to integrate it across the whole bounds of support, and I'll write it down like that, pi theta d theta. And since we're not in measure theory class, I'm going to say this is equal to infinity. But you know that what I mean is that it diverges. So if I take some sort of limit somewhere, that thing is diverging. So possibly an arrow is the better way to do it. I personally just don't care. You know what you do. So it's not that type of class where you're going to get marked off if if you use your mathematical grammar a little bit wrong. Saying that, if you divide by a matrix or something like that, I'm going to freak out. So you have to do operations that you could actually plug into a computer, and it would understand everything. So you're never going to punch this number into a computer. Okay, so basically it just means it diverges. Integral diverges. Now we confronted one of these last time. So for our normal mean example, so for this example, pi mu given x in sigma squared, we chose pi mu was equal to a normal with some parameters mu naught, sigma naught squared as the conjugate prior. Okay, I should rephrase that. We didn't choose anything. So it is the conjugate prior. And there's no other one. So, and sigma squared naught going to infinity makes this improper. do we deal with that prior? If you just think about a normal distribution that's centered at some value, I'll say mu naught, and it's got some variance, sigma naught squared. As we make this thing bigger and bigger, let's make it a little bit bigger, it looks flatter as this gets bigger and bigger. So this is a different sigma naught squared. So I'll call it star, it's bigger. And as I take that thing all the way out to infinity, again, this is a concept, it's going to flatten it perfectly. The trouble with it is that since it's infinitely wide and infinitely flat, it can't be normalized. So we need an infinitely small height so that that thing integrates to 0, or integrates to 1 across the whole domain of the function. And so that's improper. So as sigma naught squared goes to infinity, we can at least think about the shape, the kernel of the distribution. So I'll say pi mu is going to be proportional to a constant. And mu is going to live between minus infinity and infinity. And this is improper. So now for the mathematicians in the room that are bothered by this, what you're going to be thinking about is a limiting sequence of conjugate priors that you're tending towards this, but you never quite get there. You're describing what happens in the limit, if that makes you feel better. So saying that, if you just start with this, and that's what most people do, is they just write this thing down, it's a flat prior. It's flat because it's flat. It's perfectly flat. So I should say flat prior. Again, it's improper. If you apply Bayes' theorem to that, it's not actually what Bayes said. So Bayes said you have to apply this form to probability distributions. So if that really hangs you up and you're like, this improper thing isn't a probability distribution, what the heck? Then you can be the mathematician and think about the limiting sequence of things, and maybe that makes you feel comfortable. I don't know why that makes people feel comfortable, but I guess measure theoreticians say, yeah, that's okay. If you're an engineer, again, you're just thinking about likelihood times prior, and the resulting thing should be a probability distribution. You're going to interpret everything on a scale of 0 to 1, and you're just placing flat prior beliefs on everything. And I think that's okay too. I like being able to jump back and forth and accept both understandings. One's more of a little bit of an engineer's understanding of it, and one is a very technical way of thinking about it. I'm just kind of curious, does this bother anybody to do this, using improper priors, improper distributions? I remember just being so uneasy about it. It just perplexed me. It was something totally different from anything that I had ever seen. And so if it perplexes you, I guess keep thinking about it. But the real proof is in the pudding. What's the posterior distribution, and do you like it, and do you like the properties? And that's what I think we should be thinking about. Is at the end of the day, we're going to come up with answers and quantifications of uncertainty. And the question is are they good? And you see a lot of people that are doing things that are rather Bayes-esque and not saying it's Bayes. I don't get too hung up on it. I just really want to see what have they done, how did they come up with it, and what are the results of all of that. I also like having a paradigm that I can think about. Like, how do I go about business? And Bayes gives us an operating procedure for going about business. And Bayes does a couple good things. It takes into the account the joint relationship always between all the parameters and the data itself through the likelihood function. So it's describing that joint relationship. I like likelihood functions because of that. And it turns everything into a probability distribution. So I like thinking of things between 0 and 1 because I know what's big and I know what's small. And I do like the prior because it can regularize. So in the beta binomial case, it was kind of penalizing what happens on boundaries. And that's a rather good idea. So there are people that call themselves penalized likelihoodists, regularized likelihoodists. In Bayesians, or in some sense that, they take it one step further by thinking about posterior distribution and interpreting it as a probability distribution because it adheres to Kolmogorov's axioms. It adheres to what should happen in a probability space. And so for all those reasons, I don't have any problem with this. So, but it is a little bit weird. I can still kind of imagine it's a little bit weird, but when you think about it, everything you're not adjusted to is a little bit weird. So keep thinking about it and it'll become less weird. Warren.
Does this happen with every distribution? Like as you increase the variance, it's just going to get flat?
I mean, that's what happens with distributions when you increase the variance, right? It flattens out. Right. So saying that, if I wanted to create, let's just think about this. Here's a question for you. If I wanted to create a distribution with maximal variance on the interval 0, 1, what distribution would that be? Yeah, so we just fooled ourselves. Everybody thinks it's uniform, right? It's actually the Bernoulli. Yeah, exactly. It's the 0 and the 1 way over here and nothing in the middle. So maximizing the variance isn't going to necessarily come from a flat distribution. Okay, so there's at least a counterexample for you. But yeah, as you end up taking variances and you make the distribution more and more diffuse, you're taking the bumps out of it. So it's a little different than maximizing the variance. And so just keep in mind, we don't have a separate parameter in the Bernoulli model to control variance. It's all controlled through P. So I think this might be a little bit unique. But I think you're thinking about things right.
Is this essentially a uniform prior, but is the unbounded?
Yeah, exactly. So, yeah, I think so. So this is the uniform prior on mu. But it's uniform between negative infinity and infinity, and good luck dealing with that on your computer. You know, because it doesn't actually really exist. So you can't generate numbers out there. So, but yeah, pi mu. In the way I usually write it, I could pick any arbitrary constant. Still the same thing. Keep in mind what happens in the posterior is I'll have that constant in the numerator and the denominator. So, and they'll cancel each other out. So if I use the number 10, they'll cancel each other out. So again, let's just write down what Bayes' theorem looks like. Pi mu given x, sigma squared, it's going to be equal to, give myself a little bit of room. Equal to likelihood times our prior pi mu divided by the integral of that thing. Likelihood mu given x sigma squared pi mu d mu integrate between negative infinity and infinity. And if we think about plugging in a 1 right here, those 1s cancel each other. If I made it a 10, it would cancel each other too. So it has no impact on the inference. When we get to hypothesis testing, this will no longer be the case. So if you do pick something arbitrary, make sure it vanishes. So in hypothesis testing, this doesn't happen. So we're going to have another conversation once we get there. And that's at least in like 6 weeks down the line. Right now, we're just doing inference on parameters. That stuff usually makes me a lot more comfortable than hypothesis testing. We'll talk about all the issues and quirks there, and how a Bayesian handles this, and what kind of priors do they use in that case. But yeah, I would say this is uniform. So I usually write it down like this: proportional to 1, i.e., uniformly distributed. It's also improper. Our resulting posterior was normal x bar sigma squared over n, and you come up with that on your homework. And so I like the answer. That answer I'm totally comfortable with. Now some of you might think, well, that's the same thing we use in classical stats, normal x bar sigma squared over n, so I didn't get anything new out of being a Bayesian. And you didn't. That's right. I guess the only thing you got was now you can say to your Stat 101 teacher, if you built a 95% interval, you could say, no, I actually believe U is in there with 95% probability. So that's the only thing you got out of that. Later on, you're going to get a whole bunch more from Bayes. In some cases, the answers coincide, and that should give us comfort. And in some cases, our answers are totally different. Okay, any other questions about improper stuff? We'll do another one today. We'll introduce another improper prior, but I will say, for the most part, this isn't 100% true, that in spaces that are not compact, i.e. they're infinite, they're unbounded spaces. So in unbounded spaces, in one dimension, your typical reference priors or priors that everybody can agree upon are usually improper. As you get into hierarchical models, where the parameters kind of interact with each other, that won't be true necessarily. Okay, because there'll be a tug of war on some parameters. If I think about a hidden Markov model where there's two variances, I need to be a lot more careful about how I put priors on those variances. So, stuff for the future, just like in every class. Okay, let's do a new problem, just to get the hang of this. We'll play around with this problem for another couple days and just see lots of little nuances, things that we can get out of a distribution that we're familiar with. So again, we're going to have x ops, our one data point from our normal model, as mean mu and variance sigma squared. So I get that one data point, and then I know what the sampling distribution looks like. The sampling distribution looks like this. F of x obs, if I plug this thing back in, mu, sigma squared, sampling distribution is this. 2 pi, sigma. And if you want sigma squared lying in there, I'd probably put it right under the brace so I can see sigma squared up here. E to the minus 1/2 x obs minus mu squared over sigma squared. So that's our sampling distribution. Let me write down the likelihood function for mu. This is what we did last time. Then I'll show you what the likelihood function for sigma squared is. So this is the sampling distribution. What's random? This thing is. So it's a random variable, and that has certain properties. It means that it lives in a probability space, and I can measure its probability. So what does it mean to be measurable? I can stick a measuring stick on it and measure it. I.e., I have a probability model, and I can tell you how much probability mass is in certain areas. Okay, the likelihood for mu looks like, usually write it down like this. We'll just put in x obs, sigma squared. And this is going to be proportional to 1 over 2 pi. I can plug my sigma squared right in there. E to the minus 1/2 x obs minus mu squared over sigma squared. So it looks exactly the same, except I used a funny symbol. I said proportional to, because I can multiply by any number. And we'll notice that this thing doesn't matter right here. All the action is right here. So the kernel of the distribution is here. And this is the thing that's variable. This is fixed. So same mathematical form, but different function altogether. What does this thing look like in terms of mu? It looks like another Gaussian belt, but it's centered around this. Where this thing right here Looks like a Gaussian bound, but it's centered around mu. And they have the same sigma squared. If I had more observations, I'd just take a product of this. If they were IID observations. That's what you're doing on your homework. The likelihood for sigma squared looks like this. I'll plug in just x obs. X obs, if I had more, I'd take a product. I'm going to give you mu. That's the problem we're working with. It seems a little bit too silly, but you will use this form later on in the class. Proportional to 1/2 pi. I'll plug in my sigma squared. E to the minus 1/2 x obs. That's fixed. There's your data information. Minus mu squared over sigma squared. It looks exactly the same. And this is where all the confusion comes from, because nobody takes the time to sit there and really express the differences between your likelihoods and your sampling distributions. This is a little bit different. All the action here is here. So this is the thing that's variable. It's not a random variable yet, but it's still a variable. And so I might say it's the argument of the function, just to disambiguate it with a random variable. It doesn't have all the properties that you might get from Kolmogorov's axioms until you apply Bayes' theorem. So this is the thing that's variable. This one is a special type of variable. It's a random variable. Okay. I did get a question the other day, I'll address it, that isn't it the case that all these parameters, when I think about the sampling distribution, these are fixed quantities? Why am I applying Bayes in coming up with a random quantity for something that's fixed? It's a simple explanation. It's that I don't know it. I'm expressing its uncertainty in creating a random variable that follows Kolmogorov's axioms so I can express probabilities on it. I'm not saying it's variable in nature. I'm saying it's a mathematical random variable that describes uncertainty. So two different things altogether. Okay, so here's our likelihood function now, and I'm just going to write that down. That's our first ingredient in Bayes. Usually we have to think about the nature of the parameter itself before we're able to come up with a prior. So I want to think about this parameter, what it means to me, what's the property of this thing before I pick my prior. Now, if you are the true subjective Bayesian, you do not need to look at your likelihood or know the thing about the data. You can just come up, here's my arbitrary beliefs about this parameter, and I'm willing to express a probability distribution. If that's how you go about business, nobody will like your analyses. So it's not that willy-nilly that I can just come in and say, oh, here's my subjective belief about everything. I don't need to tell you where I came up with it. And here's my resulting posterior after I see everything. If you don't describe why you came up with your beliefs or what you're doing with it prior, I wouldn't expect anybody to listen. Okay, so it has to be a little bit more than just, I just came up with it out of nowhere. So usually you have to understand the nature of the parameter. Okay, so our likelihood for sigma squared, given x obs, I like to not write down all the stuff that doesn't matter. I like to have the stuff that matters. So this is going to look like 1 over square root sigma squared. I'm thinking about it as its own parameter. E to the minus 1/2 x obs minus mu over sigma squared. And there's a square out here. I have all my squares Okay, so this is the likelihood function. And if you forget about this part right here, you're going to be in trouble. It's going to mess everything up. Or we were able to chuck that when we were just trying to infer what mu is, and we said that we knew what sigma squared was. So now that variable appears, we better hold on to it. It's part of our answer. What kernel does this look like? Let's just ask a question. What disk does this look like?
Gamma?
Almost. In terms of sigma squared. Somebody said gamma, very, very close. So for gammas, you do see that parameter out here. There's an E, there's a minus sign, and we see that parameter show up over here. Anybody else have another guess? Inverse gamma. It looks like a gamma upside down. So let me show you what a gamma distribution looks like. So gamma distributions. Specifically, this is the gamma density. This looks like this. So I'm just going to be arbitrary. I'm going to say z is my random variable. So it looks like this. I'll say f of z, and there's a couple parameters that determine the shape of the gamma density. We usually call them alpha and beta, because we run out of letters quick. So we start first with the alpha and the beta. And I'm going to write down what the kernel of the distribution looks like first. It's z to the alpha minus 1, e to the minus beta, I'll say z, well, doesn't matter, z beta. So it looks like that. Now, I'm missing some normalizing constant in here. So my normalizing constant looks like this. Beta to the alpha over gamma function alpha. Now, I'll tell you what the gamma function is just real quick. Gamma function just appears as the thing that you're integrating. So I should tell you z lives between negative infinity z lives between 0 and infinity. It's positive. So z is positive, greater than 0. And alpha and beta should be greater than 0, typically. These are both greater than 0 as well. Of course, we're going to take a limit of this when we apply it as our prior, and we're going to make it improper. How you make this thing improper is pick these things to be zeros. So that's why usually when you use it, it's forced to be positive. Okay, so these are just our boundaries. This whole thing right here, there's nothing elusive about a normalizing constant. It looks like when I integrate the kernel of the distribution. So here's my kernel. My random variable is z. The kernel changes depending on which values I'm thinking about. So this is just going to be the integral of e to the minus z beta z to the alpha minus 1. Between 0 and infinity, integrate on z, invert that thing. That's what we use to normalize everything, just like we normally do. And if alpha isn't an integer, you can't express this in closed form. You're always going to have an integral sitting there. It turns out there's a relationship with factorials if this is discrete. So the gamma function and most of you have seen this. It's just going to be z to the alpha minus 1 e to the minus z dz 0 and infinity. And if you wanted to change the problem into this and insert that beta right there, you'd be doing a z substitution on beta. So you'd soak a beta into your z's, do a transformation of variables. An extra beta would come up in that derivative term in your transformation of variables. And you would see this thing right here, this extra term pop out. So if you wanted to transform this thing, if you already knew that, you could come up with that full form of the normalizing function. That's a typical probability class problem. So this is the gamma function. So again, we've got gamma densities. Gamma distributions are what happen when you integrate over this. And then there's gamma functions. Luckily, there's no extra gamma parameter floating around this. So this one is just a little bit less confusing than the beta. Very glad that they didn't take this to be like gamma. It's the convention. Okay. So that's what gammas look like. What do they look like? Well, they can look like all kinds of things. So, but they can look like this. So I'll say fz. Given alpha and beta, they can do this. Where this is 0 right here. This is a function of z. And so basically, there are these skewed distributions. It can come up here and asymptote into that, or it can be pulled far removed, but they typically look skewed. As you crank up these values, alpha and beta, then they will start to look more and more normal. It'll look less and less skewed eventually. And that's kind of cool. So there is this asymptotic normal thing. I think a lot of people jump to that too quickly. Bayesian just controls with their data size. So check out Wikipedia for more details on gamma distribution. Okay, so our likelihood looks like this. Sigma squared given x obs in mu proportional to 1 over sigma squared e to the minus 1/2 x minus mu x obs squared over sigma squared. And this isn't what a gamma looks like. So the z, this is the random variable here. When I'm thinking about this likelihood, sigma squared is the thing that's variable. Not a random variable until I apply Bayes, but it's showing up inverted. So I've got the alpha minus 1. So I could rescale this and put in a minus 1 by adding 1, 1, minus 1. It would be the 2 minus 1, so I could have 2 minus 1 right in here. That's another way of writing 2. So 2 would be my alpha parameter. So I could rephrase it. We'll do that trick all the time to get that minus 1 in there, subtract it off, add it back. Same thing. And so this looks like an inverse gamma. Has anybody ever worked with an inverse gamma distribution? We've got one.
Did you mean to drop the square root on this sigma squared?
Yes. So we got one. Let me just ask a different question. Anybody ever use a gamma distribution in here? More than one. Several more. It's an arbitrary convention, which one you use. And so I can think about things on either scale. something that's positive, when I invert it, it's a one-to-one function. And so I can invert to any scale I want and transform and play around. And it doesn't change anything, at least mathematically. It just changes the conventions you're used to. So instead of doing this, my arbitrary convention is to think about the precision parameter. I don't use inverse gammas either. So I don't know all their properties off the top of my head, but I do know something that's one-to-one with it. And so I could work out all the math, and then I know it, but I just don't know it off the top of my head. And you're probably going to remember one or the other. If you were in Britain, they would probably tell you right now about scaled inverse chi-squared distributions, which are members of the gamma family, or the inverse gamma family. And so another arbitrary convention, another way to talk about exactly the same thing. And I usually don't love it when a paper invokes that, because then I have to go to Wikipedia and look up and work out what's what, and then I go, okay, now I understand. You're doing the same thing I would do, but you just say it differently. So we're just going to pick one convention, and at least in the US, this is the one that we use all the time. So again, arbitrary. Think about the precision. So this is B is equal to 1 over sigma squared. So anytime I see a sigma squared, I can replace it with a 1 over phi and not change anything. So again, in this right here, if I take everything and I flip it upside down, I'm not really changing anything if it's one of the constants. So let's just do this. So the likelihood for phi, given x obs, is going to be looking like this. So I'll just take 1 over phi and I'll plug it in here. So this is going to be phi to the 1/2. E to the minus 1/2 times phi times x minus mu squared, x obs. And so this looks gamma. You can take this half and throw it over here, and it would look just like this. Let me ask you a question. When I take a likelihood function, and I take what were the parameters in the sampling distribution, and I transform them, do I need a Jacobian? Jenny said yes. Anybody want to say no? Yeah, it's an interesting question. And a lot of people say yes. The answer is no. And here's why. So no normalizing, no rescaling of anything. So if I just think about this distribution, our original thing, fx obs, given mu and sigma squared, this is just 1 over square root 2 pi sigma squared, e to the minus 1/2 x obs minus mu squared sigma squared. These are fixed in this form. And this is the form we use when we write down a likelihood function. So we take this thing that had fixed parameters, we throw that thing in, and then we open those up as variables. Let's just think about sigma squared for a second. If sigma squared was 5, I would just have a 5 right here. And I would have this distribution, it is what it is. If I rewrote this, and I wrote down x obs, and I wrote it down in terms of phi, which is 1 over sigma squared, I'll just remind you, eventually I'll stop reminding you what it is. Mu, this is going to look like 1 over square root 2 pi. I'm going to plug my phi. I want this inside my square root, the 5. So phi to the 1/2, e to the minus phi over 2 x obs minus mu squared. This is not squared. It's just a phi. So if I wrote it down like this, if I plugged in right here, this thing was equal to 0.2, that's 1 over 5. And I plugged in 0.2 here, it's the exact same thing. It's the same distribution, it would produce x's exactly the same. And I don't need to adjust anything. So for likelihood functions, if you take the variables and you transform them, there's no transformation, there's no Jacobian needed. However, if I do this to a probability distribution, I do need a Jacobian. Talk about that later. So no Jacobian needed. So super simple, just flip it upside down, boom, voila. If you're doing the full base thing, the Jacobian would come in on the prior, is where it would slide in. We'll look at that a little later.
Is there a reason for this? I can see that you can plug things into like one network and
So for a probability distribution, you're thinking about the space that it lives in, and you need to transform that whole space into the space. So I'll ask this question when we transform a prior later. We'll describe it. I think just comparing those two things will help you to think about it. So, too much for 3 minutes. Okay, so anyway, here's our likelihood function. My next question is which prior? Of course, the y's will have to answer. But what's the conjugate prior? Conjugate prior for phi. And we've already answered the question, so why don't you guys just launch it out in unison. Yeah. And what you have to do that is recognize this looks like a gamma. That's my first indicator. And then I just kind of imagine what would happen if I multiplied by a gamma. I would still have that gamma form. And voila, it's conjugate by definition. The answer is gamma. And I like gamma distributions because I know all kinds of things about them. Let me just ask you with respect to this problem right here, what's the expectation of z? You're close. So Stephen said alpha beta. He's remembering Casella inverter. In Casella inverter, they take this beta. Yeah, they take the beta and throw it down on the bottom. So just like an exponential, there's 2 ways to parameterize it. And so the answer here, because I threw the beta on top, is alpha beta. You'll have to get used to that.
Wait, alpha beta or alpha over beta?
Oh, it's alpha over beta. Yeah, so I corrected you and made the same mistake. What's the variance?
Alpha over beta squared.
You got it. Alpha over beta squared. There's 2 ways to parameterize this. They'll either call it the rate or the scale parameterization. And if you go to R or MATLAB, you would better be specific. Because if you think it's invoking one of them, my guess is it's invoking the other one. My experience is that more than half the time you pick the wrong one by accident. So you have to look up the way they parameterize it. So R flips this thing upside down by default. Okay, so it's gamma. So I could end up picking phi, and I'm going to pick some hyperparameters, alpha 0, beta 0, and this is going to just be a gamma. So I'll just write this down. This is going to be beta 0 to the alpha 0 over gamma alpha 0, phi to the alpha 0 minus 1, e to the minus beta 0, and I'll write phi over here. So I've kind of flipped the convention around, but it's all the same. So that's what this looks like. And we'll just finish because it only takes a minute to do this last step. The posterior is easy to recognize. We'll come back next time and we'll talk about this posterior and if it makes any sense to us. But our posterior, and I'm going to just write down, this is conditional on x odds. In mu, this is going to be proportional to the likelihood times our prior. And I'm going to write it down in terms of phi now. So I've switched my convention arbitrarily. So times pi phi. And I could write down the hyperparameter, but I'm going to suppress it. And this just looks like this. This is going to be phi to the 1/2, e to the minus phi. I'll try to make it a little bit more gamma-esque by just writing my minus 1/2 under this thing. Times, and this is going to look like, and I got rid of my normalizing constant here. Let's just look real quickly. Where are our normalizing constants here? They're right here, and I don't even need to think about them. I'm going to get rid of one set of normalizing constants, I'll get rid of all of them. All the action is here because that's what contains phi. So this is going to look like phi to the alpha 0 minus 1, e to the minus phi beta 0. And I can rewrite that down. It's phi to the 1/2 plus alpha 0 minus 1, e to the minus phi, and I'll add the stuff in the exponents. This is x minus mu squared over 2 plus beta 0. And I recognize what this is. This is a gamma, where this is the first argument, and this is the second argument, because I know what a gamma looks like. And so you can do it instantaneously if you just know what these densities look like. So this is a gamma. 1/2 plus alpha 0 x, and that's an x obs. Obs minus mu, I was given mu, so you should use it, divided by 2 plus beta 0. And this would be a fully specified answer for Bayesian to give you this big thing of probability density, where you can compute probabilities, intervals, expectations, anything you want, so long as I tell you what alpha 0 and beta 0 are. So far, we haven't discussed what are good choices for that. So let's come back next time and analyze this answer and think about what decent choices for alpha 0 and beta 0 would be. I'll give you a hint. Most people use 0 and 0, and it has an answer comes out of this very close to the answer that you probably already think about. Okay, we'll pick up next time with that. And then we're going to switch, and we're going to think about marginal distributions instead of these conditional. That's it for now. So this right here is the likelihood.
How many days do you take off after your knob?
I've been training, so not really.
You're not taking
Yeah, I mean, I was supposed to swim yesterday.
Jenny has some insight.
You go to more yesterday?
Well, yesterday I would have gone a little late.